Hello, in this lecture we're going to discuss integration by substitution. Let's start with a very simple formula. We'll go through it and then we'll do several examples so that you can get really good at this. So if you have the indefinite integral of f of, here I'm going to put a function, we'll call it g of x. You can think of this as like your inside function. And here we have g prime of x dx. Turns out this is going to be equal to big F of g of x plus c, where big F here is an antiderivative of little f. Antiderivative of little f. So why is this true and why is it important? So let me explain it and then we'll see how we can apply it to actual problems. So the key here is that g is your inside piece. So we'll let u be equal to g of x. And if we take the derivative of this using differential notation, du is just the derivative of u, and then the derivative of g is simply g prime of x dx. And now you can see that what we have here is exactly what we have here. Right, they're exactly the same, okay? So I'm going to write it over here. I'll write it in white. So we have the integral of f of, well, this inside piece here is g of x, but that's u. This is f of u. And this piece that I've underlined in red here, that's simply du. So if we're integrating f with respect to u, well, we know that's just going to be the antiderivative of f at u plus our constant of integration, capital C. That's exactly what we have up here in the formula. So this process that we just went over is called integration by substitution. And the choice of the letter u is pretty arbitrary. People typically use u. You can use other variables. You can use p, you can use w. Obviously, you don't want to use x because you already have an x in the problem. Let's go ahead and do several examples so that you can get really, really good at this. So let's try something like this. Say we have the indefinite integral of, now this one's a toy example. I want to emphasize that. So it's a little bit, yeah, you'll see. So it's going to be x squared minus 17 times 2x dx. And I say it's a toy example because it's going to be very easy. There's not going to be any manipulation involved, like nothing really tough. So let's go ahead and work through this solution. So one way to do this is to, actually, let me put a 4 here. That'll make it harder. So now the other way to do this is very hard. So one way to do this is to multiply it out. But because I just put a 4 here, that makes it very, very challenging. So another way to do this is now to use integration by substitution. So you saw above, I mentioned it a few times, that u is the inside piece. That's usually good advice. It's usually the inside function. So we'll start by letting u be the inside piece. So it's this piece here. So you write down u equals x squared minus 17, just like that. Okay, so the first step is to write that down. And then you compute the derivative, right? So this is going to be du equals, the derivative of x squared is simply 2x using the power rule, right? You bring down the 2 and subtract 1 from the exponent. So that's 2x. The derivative of negative 17 is 0, so we don't have to write that. So it's just 2x dx. And see, this is what I mean by it's rigged. You might say, well, in the previous example, it was that way too. It was, but it was the first example. Okay, so this is going to transform into the following. Use a different color here. What's the integral of? So the inside piece is u, and it's to the 4th power, so 4. And then here we have the 2x dx. That's simply going to be du. So we've taken a seemingly complicated looking integral and we've turned it into something much more simple. So now we can apply just the power rule from calculus, where you just add 1 to the exponent and divide. And that always works as long as the exponent is not -1. This is equal to u to the 5, and then you just divide by that exponent plus our constant of integration, capital C. However, we are not done, right? Because this piece here is u, so we have to go back to u at the end of the problem. So this is going to be equal to, parentheses, x squared minus 17 to the 5th power all over 5 plus our constant of integration, capital C. Really nice. And so that would be the answer to this problem. Let's do another one because that one was really easy. Let's do one that's a little bit more typical of what you might see. Let's see if I can come up with one. I have a list of problems here. Maybe I'll just take one of these because these are just a list. Let's pick something a little bit more interesting. They all look pretty easy. I'll just make one up. X. And then here we have 3x squared plus 1. Okay, that should work. And let's put a 7 here. Dx. So again, same deal. We could multiply it out, but there's a 7, so it's going to be a very, very unpleasant experience. So let's use u substitution. Again, we'll let u be the inside piece. As you can see, it's the part that's being raised to a power. That was an intentional commonality that I created between these two examples. So it's one example of the strategy. If you have something raised to a power, that's going to be your u usually, right? There's no always when it comes to this stuff, you know, for strategies, because there's so many integrals out there. So u is equal to 3x squared plus 1. All right, and then du, we bring down the 2, so 2 times 3 is 6. This is 6x, and then we have our dx here. Very good. And now you're going to notice that something is a little bit different here. So here we have 6x dx. Here we simply have, let me use red, we have x dx. And then we have this piece here, which we know is u. So there's something missing. We're missing the 6. So in my opinion, the preferred way to do this is basically you want to make this look like this. And there's other ways to show the work. You can solve for dx and stuff like that, but it's not as clean. So we're going to make this look like this. So this has a 6. There's no 6 in the integrand. So what we'll do is we'll divide both sides of this equation by 6 like this. All right, this is going to give us, I'm going to write this as 1/6 du, and that's equal to x dx. And so now we have exactly what we want. I'm going to go to yellow here so I can highlight this for you. So now we have x dx, and here in yellow we have x dx. So x dx is going to be 1/6 du, and then the inside piece is u. So let's make the substitution here. So x dx, that's this, is 1/6 du. We can pull constants outside of the integral. Okay. And then we have the u to the 7th, and then the du, right? So the 1/6 du is right here, okay? And it's from the x dx. And then the u to the 7th is here. This is one of the hardest steps for people to master when they're first learning this. I see a lot of people who, they can do the u, they can do the du, but they can't actually make the substitution. So I'm just going to go over it again, and if it makes sense to you, you are already on the way to becoming a master. So we have x dx, that's 1/6 du, and then so you pull out the 1/6. It's just a good idea to pull it out, and then you have the du here, and then this piece here, this is your u to the 7th. Now we just use the power rule as before, so we add 1 to the exponent here, so it will be u to the 8th, and then you divide by 8 plus your constant of integration, which is capital C. Okay, and this is equal to, well, 6 times 8 is 48. And then we have to go back to x, right? So u was 3x squared plus 1. So this will be parentheses 3x squared plus 1 to the 8th plus c. So this is a standard example, a little bit more challenging than the previous one because we did have to do some manipulation. You'll find that if you take a course in college where you have these types of problems, this is a very standard problem. This is something you'll probably see. And this manipulation of constants is commonplace. Let's go ahead and do another one, because that's how math is learned, right? Through lots and lots of examples. Let's do something like this. Let's do something with the fraction. So we have the integral of, let's say here we have a 7 over, and then down here we have x plus 4 to the 6th power dx, something like that. All right. So again, how do you integrate this? Well, if you just have the power rule, it's pretty tough because you have an x plus 4 here. So the idea here is to let u be the inside piece. And again, that's going to be x plus 4. So u is equal to x plus 4. In this case, the du is very, very simple. It's simply du equals dx. So nothing crazy there, pretty simple. So the derivative of x is 1, derivative of 4 is 0, all is good. So we're ready to actually make the substitution. So let's do that. So this becomes the indefinite integral. So the 7 kind of just hangs out. It's just there, over. And then this x plus 4 is your u. So this is u to the 6th. And your dx is just du. So nothing crazy there. So really a much easier substitution to make. However, perhaps the initial choice of u might have thrown you off because this one has a fraction and these other examples don't have fractions, right? And that's why examples are so important, because that's how you learn. So now to do this problem, we have to rewrite the integral. And remember, when you rewrite integrals, you always want to write the integral sign. You do it every time until you apply your rules. The reason we're going to rewrite it is because we want to use the power rule. So we want this to be written as u to a power. To do that, we'll bring this upstairs. So this becomes 7u. And when you do that, this exponent becomes negative. So this is negative 6 du, just like that. Beautiful. Now we can apply the power rule. So this is equal to 7u, and then you take the exponent and add 1. So negative 6 plus 1 is actually negative 5. Then you divide by negative 5 plus our constant of integration, capital C. All right, so this is equal to, I'm going to come over here to the middle of the screen, negative 7 over 5. And then let's take this and bring it downstairs, 1 over u to the 5 plus c. However, we are not done, right? We have to go back and actually plug in, plug in u. So u is x plus 4, remember? So it's going to be equal to negative 7 over 5 times 1 over, and this is going to be x plus 4 to the 5 plus our constant of integration, capital C. Really, really nice. So not too difficult, still pretty simple. Okay, in this example, we have the indefinite integral of x divided by the cube root of 5x squared. So let's go ahead and try to work through this solution. So in this particular case, we have an inside function. And remember, if you can identify an inside function, u substitution is something that's worth trying. In particular, if something that resembles your du is going to appear on the outside. So let's try it and let's see if it works. So we're going to set u equal to 5x squared. And then now let's compute du. So du is the derivative of u. Here we use the power rule. So 2 times 5 is 10 x, and you subtract 1 from the exponent. And then we have our dx. So this is not quite what we have in our integrand. If you look at our integrand, we actually have x dx. But down here we have 10x dx. So we have an extra 10 here, so we have to get rid of it. So to do that, we can divide both sides by 10. Remember, the goal is to make this look like what's in the integrand, okay? So divide by 10, boom. That gives us, the du over 10 can be written as 1/10 du. And then here we're left with x dx, just like that. And so now we have exactly what's in the integrand, right? We have this x dx, x dx, x dx. So let's go ahead and make that substitution. So the x dx is going to become 1/10 du. I'm going to pull out the 1 over 10. So 1 over 10. Then we have the integral symbol. And then we have just the du, right? So du, I'll put it up top. And on the bottom, we have the cube root of 5x squared. But 5x squared, that entire thing is u. This is the cube root of u. So now we have a much more manageable integral, right? This is much, much easier to work with. So this is 1/10. Okay, and so now we can rewrite this. We want to write this as u to a power so we can actually integrate it. The integral of du over, there's really a 1 here, and it's u to the 1 over 3. So this is u to the 1 over 3. Boom, really nice. Really nice. And now we can bring it upstairs and make it negative. So it's 1/10 u to the negative 1 over 3 du. All right. And so now we can apply the power rule. The power rule says that we take 1 and we add it to the exponent. That formula always works as long as that exponent is not -1. And then you divide by the results. It's going to come over here. This will be 1/10. So u to the, let's see, we're taking -1/3 and we're adding 1. So it's -1/3 plus 1. So it's really plus 3/3. So it's 2/3. When you're adding 1 to a fraction, try to think of your fraction as a number over a number where that number is the same as the denominator of your first fraction. So like if it was 1/5, you think of it as 5 over 5. Here it's -1/3. So we think of it as 3 over 3. So that's going to be u to the 2/3. And then we're dividing by 2/3. Plus our constant of integration, capital C. Dividing by 2/3 is the same thing as multiplying by the reciprocal. So this is 3/2 times 1/10. And then here we have the u to the 2/3. I'll leave it like that for now. Plus C. All right. Oh, yeah. We can multiply. 3 times 1 is 3. 2 times 10 is 20. But we're not done. We got to go back to x, right? And so what was it? U is 5x squared. So this is going to be parentheses 5x squared to the 2/3 plus our constant of integration, capital C. So works out quite nicely in this example. Okay, in this example, we have the indefinite integral of pi times the sine of pi x. Let's go ahead and try to work through this. So because we have the sine of pi x, we can't just integrate it using the formula, the one that gives us the integral of sine. So we need to get rid of the pi x. And so really we can think of it as the inside piece. So we'll make a u substitution. We'll let u be what's inside the trig function. So we'll let it be equal to pi x. And then now we'll take the derivative. So the derivative of u is du. And then the derivative of x is 1. So here, when you differentiate pi x, you just get pi, right? You just get pi, and then you have a dx. And this works out perfectly because pi dx is right here. Look at that. It's just perfect. Perfect. So this is going to become the integral of. So let's replace the pi dx. Let's replace that. That's just going to be du. So I'll put it over here. And then we have sine of u, right? Because this piece here is our u. And now when you're integrating sine, the way I do it is I try to think backwards. What's a function whose derivative is going to give you sine? Well, the derivative of cosine is negative sine. So this is going to be a negative cosine of u plus our constant of integration, capital C. And you should check your answer always. When you differentiate cosine, you get a negative sign, but you have a negative here already, and so it's going to become a positive sign. Again, the derivative of cosine is negative sign, but the double negative is going to turn it into a sine function. And so this is equal to minus cosine of u, and u was pi x. And then we still have our constant of integration, capital C. So it's always really, really important to go back to the original variable, which in this case was x. In this example, we have to find the indefinite integral of the sine of 4x. So if it was just the sine of x, we could integrate it directly. However, in this case, it's the sine of 4x. So we do have to do a little bit of work. And you could do it in your head, but I'm actually going to show the work. And to do that, we're going to use u substitution. So the first step is to let u be your inside function, which in this case is 4x. So it's inside the sine function. Now we're going to compute the derivative with respect to x. So the derivative of u is du, and the derivative of 4x is just going to be 4dx. That's because the derivative of x is 1. Same thing here, the derivative of u is 1, so you just write the du, and here you write the dx. This is called, by the way, differential notation. Okay, so now the goal is to make this look like what's up here. You'll notice that here we have a 4dx. There is no 4 here, right? So what we'll do is we will divide this by 4 so that we can make this look like what's up here. So we have du over 4. We can write that as 1 over 4 du, and that's equal to dx, just like that. All right, now it's perfect, right? Now it matches. So we're good because we have a dx and we know that's 1/4 du. So let's rewrite our integral. So this is going to be the integral of, so the dx, which I've circled, is right here. That's 1/4 du. So we can pull out the 1/4. I'll write the du in a minute. For now, let's look at this. This is sine of 4x. But 4x is u, so this is the sine of u, and then we have our du. Really, really nice. Again, the dx is du 1/4, du 1/4, and then we have sine of u because u is 4x. At this point, we just have to integrate sine. So if you haven't memorized, that's great. If you don't, you can just choose to think backwards. What is a function whose derivative is sine? Well, the derivative of cosine is going to give you negative sine. So this should be a negative cosine. This is negative 1/4 cosine of u plus our constant of integration, capital C. And you should check your answer, right? If you differentiate this, you should get the integrand. The derivative of cosine is negative sine. There's already a negative here, so you're going to get a positive sign. And the 1/4 kind of just hangs out. We're not done though, right? Because we have to go back to our original variable in the problem, which was x. So our u is 4x. So in the next step, all you do is you simply come back here to where the u is, and you put the 4x. So 4x, and don't forget the plus c, which is your constant of integration. Really simple example, but worth knowing how to carefully do the work. There is work involved, as you see. You could do it in your head. There's other ways to do it. This is just the way to do it with u substitution. In this example, we are going to integrate 1 over theta squared times the cosine of 1 over theta. Let's go ahead and work through this solution. So we're going to make a u substitution, and to do that, we're going to let u be the inside piece. So if you don't see the solution right away, it's okay. You can just try something and hope it works. So we're going to let u be equal to the inside piece, so the part inside the trig function. So we'll set u equal to 1 divided by theta. Okay, now we have to differentiate this. And so in order to do that, it might be better to take this theta and bring it upstairs so that it's written as theta to a power. This is really 1 over theta to the first power. So when you bring it upstairs, it'll be u equals theta to the negative 1. The exponent becomes negative when you bring it up. Now we're ready to integrate. So we'll take the derivative of both sides using what's called differential notation. So the derivative of u is just 1, so this is just du. Here we'll use the power rule, we'll bring down the -1, negative theta, and then subtract 1 from the exponent. So -1 minus 1 is -2, and then we still have the d theta. Very nice. And the goal is to make this look like what's in our integral. So let's go ahead and try to do that. We can start maybe by bringing this back downstairs. So this is du equals -1 over theta squared d theta. And oh, we have a negative here. We don't have a negative in the integral. So if we multiply both sides by -1, we'll basically get negative du equals 1 over theta squared d theta. Perfect. So now we have exactly what we want, right? Let me just show you here. Let me highlight it. So 1 over theta squared d theta, that's this right here. So the blue boxes match. So now we can make our substitution. I'll write it over here. So the 1 over theta squared d theta is going to be negative du. So I'll pull the negative out like that. And then we have cosine of u, right? Because u is this piece here, right? This is u. And then here we have du. So again, the stuff you see here in the blue boxes is this. See it? So it's 1/3, 1 over theta squared d theta, and that's equal to negative du, which I've put out here, or here, you see it here. And then it's just cosine of u. Perfect. Now we're ready to integrate. So if you have this memorized, the integral of cosine, that's good. You don't, just try to think backwards. What's a function whose derivative is cosine? Well, sine. So this is negative sine of u plus our constant of integration, capital C. Really, really nice. And we're not done, right? We have to go back to the original variable, which in this case is actually theta. We said u is 1 over theta. So this is negative sine of 1 over theta plus our constant of integration, capital C, and that would be the answer. Hi, in this example, we are going to integrate x times the cosine of x squared. Let's go ahead and work through this solution. So when doing problems like this, it's a good idea to try to find a substitution. In this case, our substitution is going to be the inside piece, which is x squared. So we'll start by trying that. So we'll let u be equal to x squared. And then we'll compute du. So basically, we're taking the derivative of both sides. On the left, we simply get du. On the right, we use the power rule for derivatives. So you bring down the 2, you get 2x, and then you subtract 1 from the exponent. So 2x to the first power dx. This is called differential notation. Okay, the goal is to make this look like what's up here. So up here, we have an x and a dx, but down here we have a 2x dx. So we have to get rid of the 2, and we can do that by dividing by it, like that. So these cancel. So we're left with 1/2 du, right? We can write du over 2 as 1/2 du, and that's equal to x dx. Very nice. At this point, we're ready to make our substitution. So I'm going to switch colors here. So we have the integral of, let's focus on the cosine first. So cosine of x squared is really cosine of u. Okay, it's cosine of u. So we're left with the x and the dx. So what happens with that? Well, we work that out here. That's just 1/2 du. So here I'll put the du here, and then the 1/2 really goes here. But because it's a constant, you can pull it out and write it over here. All right, now we're ready to integrate. So we're looking for a function whose derivative is cosine, right? Because we're anti-differentiating. So basically sine, because the derivative of sine is cosine. So this is 1/2 sine of u, and then plus our constant of integration, capital C. And you should always check your answer, right? The derivative of sine is cosine, so all is good. We're not done. We still have to go back to the original variable of integration, which was x. So this is 1/2 sine, and then recall that the original variable here is x, so u is x squared. So just put an x squared here. And then we have our plus c, which is our constant of integration. In this example, we're going to integrate sine of 2x times the cosine of 2x. Let's go ahead and work through this solution. So there's actually various ways to do this problem. You can use a trig identity right from the beginning. You can make a u substitution, and there's various u substitutions you can make. Let's try to think here. If we let u be equal to 2x, that's going to be okay, but then we're still going to have sine and cosine. So that's not maybe the best approach. If we let u be sine, the derivative is going to involve cosine. That's pretty good. If we let u be cosine, the derivative is going to involve a negative sign. That's also pretty good, but it introduces a negative. So I think that maybe the easiest way is just let u be equal to sine 2x and go from there. Let's try it. So taking the derivative here, we have du equals. This derivative requires a chain rule. The derivative of sine is cosine, so you take the derivative of the outside, which is the sine function, so cosine of 2x, leave the inside untouched, and then times the derivative of the inside. Your inside function is 2x, its derivative is 2, and then we have dx. This is really nice because we have a cosine 2x and a dx in the problem, and we have that here now. However, there's a 2 here, and there's not a 2 in our problem. So the goal is to make this look like what's up here. So basically, we have to get rid of this 2, right? Because there's no 2 up there. So boom, that goes away. So we have du over 2, which we can write as 1/2 du. And that's equal to cosine of 2x dx. Boom, really nice. So cosine 2x dx is right here. Let's make our substitution. I think I can actually just squeeze it in right here. So the integral, we have sine of 2x. So this whole thing is u. And then we're left with cosine 2x dx. Well, what's that? Well, it's 1/2 du. So this is just 1/2 du. Pretty amazing how it cleaned up, right? So sine 2x is just u, and then cosine 2x dx, well, that's just 1/2 du. All right, now we are pro. We can integrate this using the power rule. Basically says this is 1/2. You add 1 to the exponent, so that's going to be u squared over 2, and then plus c, which is our constant of integration. So this is going to be equal to, I'm just going to come over here, give myself some more room. 2 times 2 is 4, so this is 1/4. And then u was the sine function, so it's really sine 2x quantity squared, like that, plus c, right? You want to go back to the original variable of integration, which was x, right? There's x's here, right? There's x's, so we go back to sine. You can write this a different way. You can write this as 1/4 sine squared of 2x, and then plus our constant of integration, capital C. And again, other ways to do this problem, you can let u be cosine, and you can also use a trig identity. In this example, we are going to integrate 1 over the square root of 2x. Let's go ahead and work through it. Solution. So we'll start by making a u substitution. We're going to let u be the inside piece here. So u is equal to 2x. And then we'll take the derivative of both sides. So we have du equals, and then the derivative of x is 1. So this is 2 dx. At this point, you want this to look like what's up here. So You don't really have a 2 hanging out up here. So let's get rid of this 2 by simply dividing both sides by the 2. That leaves us with du over 2, and that's equal to dx. All right, and we can write this in a more convenient way. We can write this as 1/2 du equals dx. Okay, so this is going to be equal to, let's go ahead and make our substitution. So we have on the bottom here, we have 1 over the square root of u, right? That's just replacing this. And then the dx is 1/2 du. So I'm going to pull out that 1/2 and put the du over here like that. So yeah, looks pretty good, right? So dx is 1/2 du, and just put the u there. Okay, so we have to integrate this. So we want to write it as u to a power. So maybe as a preliminary step, let's write that square root of u as u to the 1/2. So this is u to the 1/2 du. And then you can take this and you can bring it upstairs. So it'll be 1/2 integral u to the negative 1/2 du, right? Just bringing it upstairs, and that makes the exponent negative when you do that. Now we can apply the power rule. So this is 1/2. Remember, you take this number and add 1. So 1 plus negative 1/2 is 1/2. And then you also divide by the result. That's called the power rule. You just always add 1 to whatever is there. And then plus our constant of integration, capital C. Oh, look at this, they cancel. So we have u to the 1/2, which is really the square root of u. But what was u, right? U was something that was important. It's 2x. So we have to go back to the original variable. So this will be the square root. This will be the square root of 2x plus our constant of integration, capital C. And that would be the answer. In this example, we have to integrate x times the sine of x squared solution. So we'll start by making a u substitution. We're going to let u be the inside function. So in this case, our inside function is going to be this piece here. So we'll let u be equal to x squared. Now we're going to take the derivative of both sides of this equation, and we're going to use what's called differential notation. So the derivative of u is 1, so we just write du. And then here, it'll be 2x, right? Power rule from calculus. You bring down the 2, subtract 1 from the exponent, and then dx. All right, so the goal here is to make whatever we have here look like what's in our integral up here. So down here, we have 2x dx. Up here, we have x dx. So there's no 2. So what we'll do is we'll get rid of this 2 down here to make it match what's up here. Because this is being multiplied by 2, all we have to do is divide by 2, divide by 2. So this is going to be du over 2, which is really 1/2 du. And that's equal to x dx. Very nice. All right, let's go ahead and do our substitution. I'm gonna switch colors here. So our sine of x squared, that's going to be sine of u, right? Because we know u is equal to x squared. So just basically putting a u there where the x squared is. So we're left with a couple things here, right? We're left with this x and this dx. But that's here, and we established that that's 1/2 du. I'm going to go ahead and put the du here, and then bring the 1/2 outside like this. And so now we're ready to integrate. We're trying to integrate sine. So if you have the answer memorized, that works. If you don't, you can always think backwards. Remember, we are integrating, or in other words, we are anti-differentiating. So to anti-differentiate, we think backwards. What's a function whose derivative is sine? Well, the derivative of cosine is negative sine. So this is going to be negative cosine. So this is negative, the 1/2 hangs out, cosine of u plus our constant of integration, capital C. And you can check this, right? The derivative of cosine is negative sine. There's already a negative here, so two negatives make a positive. And we're not done. We're not done. We got to go back to the original variable. So this is negative 1/2 cosine of, and then u is equal to x squared. So this is cosine of x squared plus our constant of integration, capital C. Really nice. Yeah. In this example, we're going to try to integrate cosecant squared of x over 2 solution. So if it was just cosecant squared, we would be able to do it just simply by thinking. However, it's the cosecant squared of x over 2. So we should make a substitution to make it look a little bit better. So the natural choice is to let u be this inside piece here. So we'll set u equal to x over 2. Really nice. And now we have to differentiate this. It might be helpful to think about this as follows. This is u equals 1/2 times x, right? Because it's the same thing. It's really x over 1, so this is the same as this. And now when you differentiate du, it's the derivative of u, which is just 1. Derivative of x is 1, so we just get 1/2 dx. So much easier to think about it for most people by performing this, this little first step here. The goal is always to make this look like whatever is up here in your integrand. However, down here we have a 1/2 and up here we don't. So we have to get rid of it. So let's maybe multiply by 2. So I'll put a 2 here and a 2 here. Boom. So this is 2 du equals dx. Really nice. All right. Beautiful. So now let's go ahead and make the substitution. So we have the integral and we have the cosecant squared. So cosecant squared of, let me just write the 2 again, of u, because the inside piece is u. That takes care of all of this. And then as for the dx, well, that's right here. That's 2 du. So here's the du. And let's go ahead and pull that 2 outside of the integral. Remember, you can pull constants out all day long. You just can't pull variables out. All right. So now well, you can't pull variables out that you're integrating with respect to, right? So if you have like a dx here, you can't pull out an x. You have a du here, you can't pull out a u. Constants you can pull out. So we have to integrate this. So what's a function whose derivative is cosecant squared? Well, the derivative of cotangent is negative cosecant squared. So this is going to be equal to negative cotangent of u plus our constant of integration, capital C. The 2 just hangs out. And you can check this, right? The derivative of cotangent is negative cosecant squared. There's already a negative here, so it'll become positive. We're not done though, because we still have a u here in the problem. So what we'll do is we'll go back to x. So this is negative 2 cotangent of x over 2 plus our constant of integration, capital C. Remember, it's always really important to go back to the original variable of integration when you're doing these substitution problems. The original variable in this case was x. In some instances, you might make more than one substitution. In that case, you still want to have to make your way back to the original one, which the problem was stated in. In this example, we are going to integrate the square root of the tangent of x times the secant squared of x. Solution. So a u substitution seems like something that is worth trying. And typically when you're looking to make a substitution, u is typically your inside piece. So in this case, letting u be the tangent function is a really good first attempt. So if we let u be equal to the tangent of x, then du, taking the derivative of both sides, well, the derivative of tangent is secant squared, so this will be secant squared x, and then we have our dx here. All right, and that's exactly what we have here, right? Secant squared x dx. So it works out really nicely in this problem. So despite it looking a little bit intimidating, it's actually very, very easy. This becomes the integral of, so it's the square root of tan x, so it's just going to be the square root of u, right? Replacing u with tan x. And this whole piece here is just du, so really, really clean problem, so du. So this is equal to, so to integrate this, we want to write it as u to a power, so we can apply the power rule. This will be the integral of u, and the square root of u is really u to the 1/2 du. If you ever forget, there's a number here and there's a number here. The 2 is implied, and it's always this number over this number, okay? It's always this one over this one. Now we can integrate using the power rule, which basically says we add 1 to the exponent and divide by the result. So 1/2 plus 1 is 3/2, right? Because it's 1/2 plus 1, which is 1/2 plus 2/2, which is 3/2. Boom. So this is going to be u to the 3/2, and then you divide by 3/2. But instead of dividing by 3/2, we can multiply by the reciprocal. Same thing. And then plus c. Almost done. We have to go back to our original variable, which was x. So this is equal to 2/3 tangent of x to the 3/2 plus c. And you could leave it like this, or you could write it using the shorthand notation that people often use for trig functions. It's 2/3 tangent, and then you can put the exponent here, 3/2 like this, and then an x, and then plus c. I don't really think it matters too much.